Hi, today we'll learn about how to analyze the time complexity of an algorithm. As we know, we won't find the exact running time of an algorithm because the exact running times is depend on the computer architecture, programming language, and type of variable that you declare. So we do like a asymptotic notation to like approximate algorithms. And because when we analyze in an algorithm in details to find the exact running times, it also take huge amount of times. And if we don't create a hardware or create something into an architecture, normally we won't analyze that. And we will do asymptotic notation like big theta notation, big O notation, and big omega. And each asymptotic notation has the definition like this. Okay, I will show it on the graph. So, big theta, in big theta, okay, in big theta. So, what does it mean? If this is your algorithms and has running time equal to fn, big theta will have the another algorithms, the other function which it depend on n. N is the size of input. Because we analyze an algorithm time complexities depend on the size of input, because normally when the size of input increase, the time of operation in the an algorithm will normally increase. So we will define in terms of the size of input n. Okay, so if your running time is equal to fn, there are cgn and c2gn and c1gn, which c2gn is normally use more time. This is time. Use more time than your algorithm, and there is a c1gn, a function of the input of size n, which always takes less time compared to your running time fn. And this is true since the started and zeros. Okay, and why we do like this is like if you want to go from CMU to Maya, right? If the exact time is like 15 minutes, point 30 seconds, 7 minutes, and 15 minutes and 37 seconds, okay, which is in super details, right? So, but if you say that to go from CMU to Maya, it takes not more than 16 minutes and or use more than 14 minutes, right? It bound your times, right? It close to your times, the exact time to go from CMU to Maya. However, it's close, right? But it's more easier to understand, right? And to find, right? The asymptotic notation is like this. You won't find the exact running time because it depends on the programming language, computer architecture, the variable that you declare. But we will approximation it, the upper bound and lower bound, right? That your algorithm will not use more than the upper bound time or 16 minutes, and your algorithm will not use less than the lower bound time 14 minutes. Okay, and in real things, right, you may tell your friend that it takes at least 1 minute, which is true, right? Or at most 2 hours, which is true, right? However, it's not close to your times, right? We did the pink one, right? But it is true, it bound and it follow the asymptotic notation definition. However, the green one is the loose bound, which means it more far from your running times, and the blue one is the closer time or tight bound, which is close to the time of your algorithm. Okay, and big data will have both upper bound and lower bound. Upper bound defined in terms of C2GN and lower bound defined in terms of C1GN. And it is true, the bound is true since the started input side n zeros. And you see, big O, right? This is your function. And you have just only the upper bound, right? So, upper bound inform you that your algorithm running time will not use more than that time. The more time this means the worse time, right? So it is worst case running time bound, okay? And from big data, this is your function, running time function, and this is the bound, right? Which is always used less time compared to your exact running time function, okay, with the started point and zeros. So it always use less than, right? And less mean faster, better performance. So this is the best case bound running times, okay, big omega. Okay, and this is the concept of asymptotic notation. Thank you.